As I said before, there's kind of a series of steps that we go through for all of this. So, second law problem. And I want to remind you that first law problems are problems that cover any situation in which your object is stationary or moving at a constant velocity. Second law problems cover situations in which your object is accelerating and also is the default in case you don't know. Like maybe the problem doesn't say. The problem tells you about things that are happening but doesn't indicate whether there's an acceleration or not. You have to assume it's a second law then. So our book, can we all agree we're looking at a first law problem? The book is not moving. It's stationary relative to the table. So, let me give you a brief overview of the series of steps and start with that. Because although we got started, we didn't go through the entire set. So I want you to know what the overview of the set of steps is. And although I'm numbering them, I hate the fact that I'm going to be numbering all sorts of stuff today. But first, you make your choice. Is it a first law or second law problem? The next thing you're going to have to do, and this part's tough and probably the hardest part in the beginning, is you have to draw a free body diagram. We'll spend most of our time today drawing a free body diagram. We'll also do this part, apply a coordinate system. This has its own ups and downs, and we're going to see right away that applying a coordinate system might be the one that challenges you the most. You're going to resolve off-axis forces. Into their components. I don't know why they're both number 3. So let's make this one number 4. And then you'll break your problem up. You'll then break your problem up into one-dimensional problems applying Newton's laws. I know that's way down at the bottom. Some of you can't see it. So, there, now you can see it. Just trying to go quick. That's the overview. We made it all the way to to just free body diagrams yesterday, and I was listing out forces. So we're gonna kind of pick back up the same way we kind of started yesterday. I'm going to throw out examples, and we're going to go through this series of steps. Does that make sense? All right. So we didn't make it past here, but you really can't talk about these until you've got this sitting in front of you. So that's why I spend so much time. And then under this is where I was listing all the forces, because that's really part of drawing a free body diagram. So today, although this is going to be a little ridiculous, we're going to start with our first example. Inventory is to ask whether you think it's a first law problem or a second. Next step is to apply a coordinate system. The next step says to resolve off-axis forces into components. Break problem up into one-dimensional problems applying Newton's laws. And I know it's a ridiculous example, and first period thought it was a lawn fest until the moment we went to example number 2, and all of them did it wrong. So it might seem like a yawn fest, but listen, I'm choosing something easy because I need you to see the full extent of what you have to do. And then after that, you'll understand right away that this is a different way of thinking. So we're going to start with probably the most mundane and boring example I can come up with, and that is a book resting on a table. So here it is, book resting on a table. The first thing I said you had to do, according to the force concept, what I usually tell everybody to do is once you know you're dealing with a first law problem, just write up somewhere at the beginning of the problem that you're going to be using Newton's first law for it. So I'll write summation of F equals 0. The very next thing you're going to do is draw a free body diagram. There are several steps to drawing a free body diagram, and this is the one that takes probably the most kind of introspection. First, each object is represented as a dot. So each object with mass now, there can be lots of objects in a problem. And I know you're thinking everything has mass. In special physics land, some things have mass and some things have so little mass they don't count. So if I'm using a piece of thread to hold two things together, I might not include the mass of the thread. If you're told in a problem that something is massless, what you're really being told is that it's too small to matter. Does that make sense? Everything really does have mass. But we worry about the things that we're supposed to focus on. So if I have a 60 kilogram box and I have a 1 gram pulley, I'm not going to worry about the mass of the pulley interfering with the 60 kilogram box. Does that make sense to all of you? So that's the deal. So anything that has mass gets its own dot. We're dealing with only single body problems. So for the time being, we're going to focus on the object at hand. So this is just the book. So I will draw a single dot representing the book. We're next going to draw arrows that represent each of the forces acting on the object. These arrows should be drawn from the dot, they should be drawn starting at the dot and drawn away. So you draw these forces starting at the dot and drawn away in the direction of the force. Second, the arrow should be drawn to scale. Is there anybody who does not know what drawn to scale means? It means that when you draw the arrows, their relative size in the picture should match up with what's given in the problem. So if they tell you that one force is half the size of another, then that arrow should be half the length of the other arrow. Now, you're very seldom given that kind of specifics. You often have to kind of think through what it would take to make the arrows to scale. You're guided by whatever law you chose here. So if you chose that it is a first law problem, then the forces have to be balanced. So for everything that pulls upwards, there should be an equal amount pulling downwards, and everything pulling to the left, there should be an equal amount pulling to the right. So you may have to be thoughtful about that and considerate about how long you draw each arrow. You may not get specifics about their size. You're trying to get close. Now, drawing a free body diagram, this is what the rules are, but now we need to talk about, well, what are our options? What arrows should I be looking for? So let's go through the arrows. Oh, I don't want to do that. How can I do this? I can do this. There we go. So we have a group of forces that we're going to use. This is not an exhaustive list. There are other forces, and I will even add to this list today. But we're going to break them down into 3 broad categories. The conservative or fundamental, I'm supposed to say interactions, but they're forces. We talked about those yesterday, right? Gravity, electroweak, and strong nuclear. I'm only going to list gravity as it's the only one that matters in this class. We're going to call gravity weight. Now, after that, we're going to have contact forces. There are lots of different kinds of contact forces, but they have to live up to their name. Contact forces have to be forces that are in contact with the object. They are applied because something is touching the object. For the time being, we only have 2 of them to work with, but I'll be adding to this list. There's normal forces, and there are tension forces. I'll be using a capital N for normal and a capital T for tension. An object can have multiple normal and multiple tensions. It can be in contact with more than one surface, and it can be in contact with or have more than one string attached. But this one, these are always perpendicular to the surface. And these are always in the direction of the rope, string, etc. Tension is going to have something that's connected to the object. But basically, normal forces push and tension forces pull. And last, resistive forces. There are 2 resistive forces that we'll worry about. There's friction, and there's air drag or air resistance. Generally, I use a lowercase f for friction, and drag, I might use F with a D on it, or I might just use D for drag. I know that's really close to the bottom of the board. That's what we're talking about. Now, I can't fit this here, and I will write it in a minute, but friction is a force that prevents one surface from sliding across another. Friction is a force that attempts to prevent one surface from sliding past another. Friction is a force that tries to prevent one surface from sliding past another. We will find that there's 2 kinds of friction. There's one that holds something in place and one that acts to try and prevent something while it's moving. So we have a stationary version and a moving version. All right, let's deal with our book problem. Now, we're just trying to apply these rules in a simple, straightforward case. The book. Can we all agree that there is a conservative force acting on the book? When you're asked if there's any conservative forces acting on your object, be the first one to say yes, because that's always going to be true. There will always be the gravitational force acting on our objects. So we start by drawing a force that is straight down, and we list it as capital W for weight. What you draw for weight generally sets the scale for the rest of your forces. Everything else is going to be relative to this. So whatever arrow you draw here, be careful of its size, because everything else is going to be balancing out the weight. Now, every force has some properties associated with it, but some forces have a specific way of calculating them. Weight is one of them. Weight is the product of mass and gravity, the acceleration of gravity. So weight is always mg. And I'll sometimes write just mg instead of weight. especially if there's more than one object. I might have M1G and M2G someplace else. All right, once we've handled the conservative force, we go on to the contact forces. Is there any surface in contact with the book? Yeah, it's resting on a table. All right, the table is a surface. The table must apply a force to the book because it's in contact with the book. Anything that touches the book applies a force. The table is a surface, so it's a normal force. And normal forces are always perpendicular to the surface. So the surface is horizontal, the normal force has to be drawn upwards. And I'm not drawing it arbitrarily. I'm pretty sure it's the table that's keeping the book from falling to the ground. So I'm going to draw the normal force so that its length is as close to the weight as I can possibly muster. I mean, you have rulers, you can make sure it's exact. But I would try and make sure that it is to scale. Now we're going to continue through this list, but I think we can go through the rest of the list pretty quick. Like, I don't see any cables attached to the book. With no cables attached to the book, I don't think there's going to be any tension forces acting on the book. And I'm pretty sure my desk is pretty level there, so I don't think I have to worry about the book sliding off the surface. I don't think there's any force in play that's trying to keep the book from sliding. Would you guys kind of agree with that statement? So I'm going to ignore friction. And air resistance is only in the problem if they tell you it's in the problem. So I didn't say anything about air resistance. We can ignore it for this problem. That's it. We have drawn a free body diagram. We've exhausted our list of forces. We have identified all the forces that we believe are acting in the system. We're not done, but we're done drawing a free body diagram. Now, if all you had to do is draw a free body diagram, you could walk away and say, I've completed this process. But we're solving a force concept model problem. So I want to go through all of the steps so you can see all the steps as they are applied. We look back. This literally means to draw over top of your system the coordinates that you will use. What is positive x? What is positive y? Now, I've seen a lot of students make crazy mistakes here. A coordinate system has two lines that are perpendicular to each other, right? That's a coordinate system. You can't draw them any way just to make them nice. You have to draw them perpendicular to each other. For this one, it's no big deal. But there is a process, and it's not arbitrary. Well, it's all going to go away. So we have room. Do that again. Apply a coordinate system. There are two priorities. These are not steps, these are priorities. You can only apply one coordinate system, and how you apply that coordinate system can determine whether you can solve the problem or not. So you have to consider priorities here. What I mean by that is, if circumstance one exists, that's your number one priority. If it doesn't exist, then choose number two. The number one priority is to align a positive direction with the acceleration. That's your first priority, is to align a positive direction with the acceleration. If there's no acceleration, or if you can't do that, then your second priority is to align the coordinate system with as many forces as possible. Okay? Those are your two priorities. So you start with one if you can do it. If you can't, you do two. Now, this example is bonehead simple. There's no acceleration, so priority one doesn't matter. But that still means use priority two. I don't want to make my x direction this way and my y direction this way, right? Priority two says to try and align it with as many forces as possible. So it seems to me like the best way to do that would be to make the x direction or the y direction this way and the other one this way. So I'm going to make this the positive y direction and this the positive x direction. That makes this negative x and this negative y. This is not part of your free body diagram. This is what you have to do to use your free body diagram to solve your problem. So we apply a coordinate system. Both of these forces are on the axis, so there's nothing to resolve. This would only matter if you had a force that was like this way. Then you'd have to resolve it. You'd have to break it up into components along the x direction and components along the y direction, but we don't have that in this case. So the last thing. So we are applying Newton's laws. Now, we're only doing first law problems right now. So this should be pretty straightforward. But I need you to kind of get in your notes what these laws actually are. This is not an equation or a formula. It's a set of instructions on what to do. First, Newton's laws are three-dimensional, but our math is one-dimensional. So when we reach this point in the problem, we've applied a coordinate system, and we will be breaking up Newton's laws into each of the dimensions. So I'll be applying net force in the x direction and net force in the y direction. Now my problem is very one-dimensional, so I'm not too worried about this step, but you need to know that that's not going to last very long. Now, that means to add up. This means all of the forces in the x direction. This little bar means to take into account their direction, which for us means plus or minus, and set them equal to 0. It's a set of instructions. So in each of the dimensions of your problem, you'll add up all the forces in the given direction, taking into account their direction, and set them equal to 0. Now, once we have the second law, it might not be 0 anymore because those problems deal with acceleration. So Newton's second law will handle that, and there might not be a 0 there. There might be something else. But we're just dealing with first law problems today. Now, this problem is very simple. So there are no forces in the x direction, so I am done. There appear to be two forces in the y direction, and the normal force is upwards, and the weight is downwards. I have added up all the forces, taking into account their direction, and now I must set them equal to 0. Now, I'm not going to write this next thing down, but you should. The force concept model and Newton's laws don't solve problems. The force concept model and Newton's laws create relationships that might be able to be used to solve problems. When you're done applying the force concept model, you will be creating a custom equation that is designed to help you solve this problem and this problem only. There is no formula like the kinematics equations that you just apply to a problem. In every one of these, every one of these circumstances, you will be making up a new equation for each situation. So at the end, you're going to have a couple of equations. From there, you're going to be doing substitution and stuff like that to try and figure out what it is they asked about. All right? We're going to do this again. We're going to do as many examples as we can fit in before the bell rings. I'm going to leave this here so I can grab these instructions every once in a while. Rules for the free body diagram. I'm going to start by just drawing out a picture of what you guys just saw. It was the calculator resting on the surface of the book, but I tipped the book up at an angle. So I pulled the cover of the book up an angle theta. Would you agree this is kind of what we saw? And we're interested in the calculator. So this is our situation. What I want you to do is draw a free body diagram that we could use to solve this problem. I'll remind you, we have rules. So let's talk about those rules real quick. You're going to take the calculator and make it a point. Then you're going to ask yourself about these forces acting on the calculator. I am not going to help you. I want you to do this. I saw it in your eyes. It's just drawing arrows, Mr. Shelton. Go for it, please. Draw me some arrows. Let's consider the rules and what we should be drawing based on the rules. The rules dictate how every arrow should be drawn. Is there any conservative force acting on the object? Yes, gravity. So the first one should be easy. There should be no mistake that everybody should have drawn an arrow downwards. That's where we're going to begin. Now, is the calculator in contact with a surface? That surface would be the cover of the book, correct? Normal forces must be drawn in such a way as to be perpendicular to the surface in contact. Pretty sure perpendicular to the book would be that, wouldn't it? So I saw a lot of you draw arrows upwards, but I don't think there's an upwards arrow here. I think that arrow would be better. So perhaps longer, because I need to make it so that the upward portion of this supports the book, but it's at an angle. We already indicated at the start of this that this is a Newton's first law problem. There's got to be balance. And this doesn't look balanced to me, does it? It looks like this object would be pulled this way based on these two things pulling on it. Was there any cables or ropes attached to the book? No tension. Do you think there is a force attempting to prevent the calculator from sliding across the surface? All right, so now we're talking about friction. Now, listen, this one I didn't say, and this is where you might be having some misgivings. So let's talk about friction for a minute. Friction attempts to prevent an object from sliding across the surface. If you want to interpret that correctly, friction has got to be directed along the surface, which means it has to be parallel to the surface. It's trying to prevent it from sliding along the surface, so that force has to be parallel to the surface. Not to mention, it's trying to prevent it from sliding across the surface. So it's got to be drawn parallel to the surface and in a direction that would prevent it from sliding. I think if you combine all of that into your head, that's got to be this way. Wouldn't you agree? Now, more than that, if you paid really close attention to the things I said, then the frictional force has to be perpendicular to the normal force. If normal force is perpendicular to the surface and friction is parallel to the surface, the normal force and frictional force are always perpendicular to each other. That will always be true. How many times do I get to say always in here? It's very seldom. This is an always. I would make sure you know this. In fact, if it were me and you really want to understand this, what I would have you write down is this: normal forces cause frictional forces. There is no friction unless there's a normal force. Normal forces cause frictional forces. There is no friction without a normal force. This has to be true because friction comes from contact with the surface. So that's it. We have completed our free body diagram. We have followed the rules, and we've made sure the rules describe the situation at hand. Now, hear me out. We want to apply a coordinate system based on my two priorities. Priority number one is to direct the positive direction in the direction of an acceleration. There's no acceleration here. Priority number two, to try and align the coordinate system with as many forces as possible. I know that two of these forces are perpendicular to each other, so I'm thinking the best way to align my coordinate system would be to align it with the two forces that are perpendicular to each other. I can choose any coordinate system I like. This one means only one force is off axis. Now look, you can actually choose any coordinate system you want. You could choose this coordinate system. But if you choose this coordinate system, both the normal force and the frictional force are off axis, which means you'll have to break each of those up into their individual components. If you choose this one, then this is the positive x direction, this is the positive y direction. Only the weight is not aligned with one of the axes, so only the weight would have to be resolved into its coordinates, or into its components. You have to make choices. This is a choice. Example 3. I'm going to apply a force from my arm to the book and slide the book up the wall at a constant velocity. You guys see what I did? So, I applied a force from my arm, and due to the combination of forces, the book slid up the wall at a constant velocity. I'm introducing a new category of force here. Called an applied force. Sometimes in these problems, they will just say, this force is acting on your system. And they'll give you the size of a force and an angle. I did that, right? My arm was pushing on the book at an angle. So when you're given a force, we call that another contact force, and we just call it an applied force. So it'd be something like this. Here's a picture of what I think we saw. Book, wall. My arm was pushing on the book. Applied forces are forces that are on your system and you just apply them the way in which you are told to do so. Could be a guy pushing on some boxes across the floor. Technically, this is a combination of things. It's a normal force and a frictional force, and we're just wrapping it up as one force. So there's an applied force acting on the book from my arm. Now, be careful. Although I drew it like this, because that's what it looked like from your vantage point as I was pushing on the book, all forces in a free body diagram originate at the dot. So when you go to draw this force into your free body diagram, you need to make sure it's acting on the mass and drawn away from it. All right, please do your best. Draw a free body diagram that describes what happened to the book. We have limited time, so I think it's time to walk through this. Are there any conservative forces acting on the book? Always. The first one. So I will draw a downward arrow, label it W. Is the book experiencing any contact forces? Well, there's an easy one. This problem gave me a force I have to use. So I'm gonna draw that in right away. I have to use that force. It was given to me. Is the object in contact with any surface? It was in contact with the board. So I need to draw a force that indicates that there's a perpendicular force given by the board to the book. The only possible way that could be is this way. Are there any ropes or strings or cables connected to the book? No. The book was sliding up the wall. Is it possible that there was a frictional force acting on the book? Friction needs to be drawn in such a way as to be parallel to the surface and oppose the direction of motion. So we have two forces that are in the same direction. There are multiple ways to do that. One is to draw both forces side by side, like I've done here. One of them is to take and draw the force stacked, like that. Both are acceptable, so you can draw it either way. I tend to favor drawing them side by side. I tend to favor taking all the forces start to center and drawn away from the dot. But neither one of them is right or wrong. Now, I'm not sure I did a great job balancing this, but my next task is to apply a coordinate system that will basically be based on my priorities. So priority number one, draw it in the direction of, draw the positive direction in the direction of the acceleration. Was the system accelerating? It was moving, but it wasn't accelerating. So I'm going to draw it so that it's aligned with as many forces as possible. Which I think looks like this, right? Only one of the forces is off axis and the other three are along axes.